Okay, good evening, everyone. Um, so last time we had started on Boolean algebra as the mathematical framework in which we can model digital logic systems, and towards the end of last lecture, I had begun to examine some of the properties of the Boolean algebra system. So recall, if you might, we had talked about that how, yeah, like our regular algebra, there are certain axioms that underlie Boolean algebra. These properties are not provable, but they are intuitively kind of obvious. So we just assert that these things are true. That in a way, this saying something about our intuitive notions of what and or and true and false are supposed to do. Um, Now, using these properties, using these axioms, there are a whole bunch of properties that you can derive, essentially statements within the algebra that you can prove. Some of them are have corresponding um, have correspondence in the regular algebra that we're used to, and others you have kind of not seen. So, like idempotence and absorption and combining and De Morgan's, these don't exist in the regular algebra. Now, uh, how do we know that these things are true? I mean, it's again, I mean, at an intuitive level, if you think in terms of true and true, yeah, it's going to be true. False and false is going to be false, and so on and so forth. So some of these things you can think of it that way. But let's try to understand. Let's take a few sample and see how we can examine them. So one version of the absorption property is that x or x and y is equal to x. That essentially it is saying that in case of the or, if one of the inputs is a more constraining input, it doesn't really matter. Now, one way we can kind of do it is by essentially exhaustive enumeration. So I can consider all the possible combination of values that x and y can take, and then I can write down what x and y is going to be. So in this case, it's going to be 0, 0, 0, 1, and then I can calculate what uh, x or x and y is going to be, and you can see it is 0, 0, 1, 1. And in this particular case, you can see that the last column and the first column are the same, and so it proves it shows that the absorption property is true. We can do the same thing with any of the other properties. So combining said x and y or x and not y is equal to x. Okay, so it's kind of basically saying that if I'm ending with both y and not y, then I'm just left with x. And again, you can kind of do the same thing. You can calculate x and y in the truth table, x and not y in the truth table, and then do the ORing, and you are going to get back the x. No, those are simple. Let's look at a more interesting one, because this De Morgan's theorem, and again, remember we had kind of two versions of them, right? So I'm just picking one, and this is an interesting one because it basically says that if I give you an expression in terms of and, then there is a way I can convert it into an expression in terms of or. So not of x and y is the same as not x or not y. And again, intuitively, if you think about it, yeah, you can think it certainly is true. But again, we can do the same truth table game out here. I calculate this, I calculate the other one, the two are the same, and therefore I have proven things. Now, this way of enumerating and then showing the equivalence certainly can work for arbitrarily complicated properties that one might imagine. The only thing is that if I have a large number of variables, then the truth table might be huge, right? The size of the truth table grows exponentially, right? So if I give you, I don't know, let's say something with 10 variables, then, well, I have 2 to the power 10 possible rows, and that's like a pretty long truth table. So probably one wouldn't want to deal with it that way, but at least in principle, you could. So enumerating the truth table is a great way if the number of variables is small. Okay. Now, what might be of interest though is if I have too many variables, that can I achieve the same things by essentially algebraic operations, not making use of a truth table. Now, going back to this De Morgan's theorem in its textual form, it's basically, like I said, it's basically saying that I can switch back and forth between an and or. Actually, if actually before we move on, so in a sense, if I go back to this expression, what this is saying is that if I were to think in terms of gates, it's basically saying that if I have a gate like this, and I'm going to use the bubble to indicate inversion, if you recall. Yeah, so this is kind of the knot. This is the same as, sorry. Again, this, I'm just not drawing the inverter. This bubble indicates not. Okay, so it's basically saying that an AND gate followed by inverter is the same as an OR gate preceded by inverters. I can kind of push the inverter from output to all the inputs of the gate, and I'm good to go. The other variant, so these two essentially, these two variants are the same. Okay. The other version of De Morgan's theorem in our table is basically kind of swaps or an AND, so the same property holds true the other way. Now, one exercise I would like you to consider doing is, can you prove this algebraically? That is, let's say I ban you from using any sort of enumeration, right? I mean, you're not allowed to list all the cases and then say, hey, for every case it is true, but rather I want you to symbolically manipulate the expressions and prove something like this is true. So this kind of problem we often face, right? I mean, I might give you two circuits that look different. They have gates, and you can, given the gates, you can write down the expression one-to-one corresponding to the gates, but now you ended up with two expressions which look different, and now you have to prove that they are the same. And of course, if you have the luxury of enumerating, you could do it, but let's say I don't want you to enumerate. So there are kind of a few strategies that one could follow. So let's say you set out to prove that some function f given abc is equal to the function g at abc for all abc, right? I mean, this is kind of for all abc in 0, 1, let's say. Okay, so let's say we want to prove that. So strategy one is you take those Boolean properties that we know, so the axioms as well as any property that exists on that page, let's say, and then you apply it to systematically transform f to g or vice versa. Now, oftentimes this kind of doesn't really work because f and g may be some complicated expression, and it's very hard to kind of come up with this transformation. So, and strategy two is in the reverse, same issue. There is another strategy which works oftentimes better. And the idea out here is that, let's say we are trying to prove that f and g are the same. Then what that means is that whenever f is true, then we want g to be true. And whenever f is false, then g is false. So one of these things, if let's say f was true, then g also has to be true for the equality to hold, and in that case this would be 1, and it doesn't really matter what the other one is. I should get an output 1. And likewise, if f is false, so okay, and likewise if f was false, then the other clause in the OR operation would be true. So does this equation remind you of any operation that we have seen before? Remember, we had talked about primary gates and secondary gates, primary operators and secondary operators. So does have you seen something like this anywhere? X and y, or not x and not y. So
is this a not XOR?
XNOR, yeah. So actually, so this is the XNOR operation, right? XOR was the two are unequal, and XNOR is the other way around. So really, what we are saying is that XNOR of f and g is equal is true. So I could do that, right? Now the reason this approach is easier is because on the left hand side I have this complicated expression, and my goal is to reduce it to 1. I have to show that for all values of ABC, the left hand of this equation is always reduces to 1. And that's usually a lot easier than going from a complex f and trying to achieve a complex g, or vice versa. Okay, so reducing a complicated thing to something simple like 1 tends to be easier. I could do the other way also. I could say f and not g, or not f and g. So this is really XOR of f and g. Okay, XOR. Okay, so we are saying that XOR of f and g is 0, which means, which is another way of saying is they are not unequal. Okay, so therefore they're equal. Again, this tends to be easier. So it's a lot easier strategically, you will find, to kind of do that when you're trying to show two expressions to be the same, that you kind of take their XOR or take their XNOR and prove them to be 0 or 1, whichever you kind of feel like doing. Whereas strategies 1 and 2, generally speaking, are going to be kind of harder. So I'm going to leave it as an exercise for you to see how try it out on some of those expressions that I have on the previous one, to kind of leave it. I'm going to make sure that these properties that we talked about out here, yeah, this one, that you can show them. But I'm going to show you a different example, a more complicated example, to kind of see how we do it. It's very similar to how you might do in a regular algebra. So let's say I give you this expression. FABC is this kind of complicated looking kind of function. And let's see how we can kind of manipulate this thing, right? So what you see are AC or ABC, or not ABC, or AB and not C, and or ABC, or I think I messed up out here. Yeah. Okay. So I've given you this expression, and clearly you can see it has some. Yeah. Go ahead, please.
Quick question: what is there two A and B and C in the function?
Say it again.
Is there
two A, B?
A and B and C? So the
twice,
second
right?
term, yeah. Is that meant to?
Yeah, this is just kind of a random example.
Oh, okay.
So I deliberately meant to have two equal things, because remember, they are basically going to cancel out, right? I mean,
oh, okay,
because
that makes sense. Thank you.
It's just to illustrate a point. Okay, so so first thing we can do is, I mean, I kind of rewritten that expression in kind of multi-line format. I can apply the absorption property. So I can take A and C and A and B and C. And remember, the absorption property basically says out here that this thing will reduce to, anyone remembers?
A and C?
A and C, exactly. So I simplified that. Then I can apply combining property for both these. So if you apply the combining property, what will happen is A will cancel out in the middle one, and C will cancel out in the other one, and this is what you're going to be left with. Okay, so I took that sort of expression and I ended up simplifying it like this. Now, obviously, there are other ways you can manipulate this expression. I would also argue that, generally speaking, going from something complex to simple is a lot easier. So this tends to be easy, whereas this tends to be hard. This is a general harder usually. Okay, which is why kind of that strategy one, strategy, the last two strategy, the XOR based strategy in the previous slide kind of makes sense. So try this out on some examples to see how you can kind of manipulate, but nothing fancy going on. You have done this thing with your regular algebra. It's just that here the operators have some additional properties. Okay.
In this specific example, are there any advantages to having the simplified versus the unsimplified, like original expression when it comes down to like the gates and stuff?
Yeah, so you would see it later on, but generally speaking, gates with fewer inputs are cheaper. So if you think that each one of the clauses in the original expression was an AND gate, right? So I was using, and even let's say even if I ignore the redundant ABC, I still needed, let's see, 3 2-input NAND gates and a 1 2-input AND gate of sorts, and then I had a 3-input OR gate, right? And here I need 3-input OR gates. That remains the same, but my AND gates are simpler. So I've certainly reduced the complexity out there significantly. So yeah, I mean, simply usually when you are trying to optimize for area or even speed or power, the first thing is to really kind of reduce the number of operations and the number of symbols your expression has. Okay, so what does this function do?
If at least 2 of the variables are true or 1, then your function is going to return 1.
Exactly. So this is what we call as majority. Okay. Majority of the inputs are 1. Okay. So now another thing I want to go after is you saw in De Morgan's theorem that I can go from AND to or to AND. Okay, and it kind of begins to hopefully give you an indication that even our basic operators have a bit of a redundancy, right? I mean, I could take an expression which was in terms of AND and NOT, and I could go into an expression which was in terms of OR and NOT. So that means I can express OR in terms of NOT and AND. So why did I need the OR operator? I don't, right? I can get away with just that. And this is what I want to explore further. So recall again, we have seen this slide before. These are some of the gates that we have in mind. Let's say I tell you, suddenly we lost our supply of NOT gates. Can you make a NOT gate out of one of the remaining gates?
Would it be something like tying the input to both inputs of like a NAND or something similar?
Excellent, yeah. So I could do this, right? So it basically says NOT of in and in, which is the same as NOT of in, using one of those properties that we mentioned earlier. Okay, I can do the same thing with NOR. Okay, how about AND gate? Can you ever make a NOT out of AND? Not really, right? I mean, if you think about it, there's no way I can ever do. I cannot do it with OR either. So with other gates, it's a little bit trickier. Okay, impossible. So not every gate can go to every other gate. Okay, so this one we saw. Okay, let's I'm just skipping things. So essentially, what we have seen this slide, this version before. Now let me ask you the following: can you make an OR gate out of NAND gates? Well, so that's the question I'm asking. Can you make them from my supply of AND and NAND disappeared, and I want to know that can I make these 2 gates out of the remaining gates, right? And I mean, clearly, if I can make, let's say, AND, then I can always make the NAND because I have a NOT already there available to me, and vice versa. So what we are going to do is we are going to use a De Morgan's theorem, which basically in gate terms says this, right? That a NAND is equal to an OR with inverters before them. So of course I can do it, right? Because I have the supply of NOT and I have the supply of OR. So I can make a NAND in this manner, and then I can make an AND by adding an inverter to the output. So I certainly can do that. Could I do an OR gate out of NAND gate? Same logic holds. You kind of just use the other version of De Morgan's theorem, which lets you do that. Okay, so I can make AND gates, the AND and NAND gates out of the other ones. And we already know how to make NOT from NAND. So what I have shown you is that using NAND, I can make NOT, and using NAND, I can make OR. So I can make OR from NAND. I can make NOT from NAND. So if I only give you a supply of whole bunch of 2-input NAND gates, you can make anything. Remember, XOR was already composed of OR and right. I mean, XOR was a secondary operation. So basically, the only if you could imagine defining an algebra, this algebra differently, where you had just one operator, NAND, and everything else can just follow from that, right? I can consistently make everything out of that. So key takeaways: set of basic operators has redundancy. One can make OR out of NOT, N, and AND. Similarly, we can make an N, blah, 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 and XOR, obviously, we could. So NAND alone can implement all the basic operations, and thus it can make all Boolean functions. Same thing is true for NOR. I cannot do this with OR alone or AND alone, because you cannot make a NOT out of AND, and you cannot make a NOT out of OR. Now, any set of gates, we will call it universal if it has a property that I can implement anything with it, right? So NAND, the set, if you were to think of the set consisting just of the NAND gate, it is universal, or a set consisting just of the NOR gate, it is universal, and so is, let's say, this, NOT and AND, right? That is universal too, and likewise, NOT and OR is also universal. Now, it so happens, interestingly, that if you look at the technology which is used to make Silicon chips, these gates, NAND and NOR, also happen to be the cheapest gates. It ironically, I mean, AND and OR are more expensive to make in technology, whereas NAND and NOR is cheaper to make. So it so happens that the gates which are universal also are actually the cheaper to make. Anyway. So this is a key takeaway, that if I give you a large enough supply of 2-input NAND gates, then you can make anything out of it. Any digital system can be made just using an infinite supply of 2-input NAND gates. So that's a nice thing to have. You can try. One of the things you might immediately ask is, hey, but what about 3-input NAND gate? Can I make 3-input NAND gate out of 2-input NAND gates? Yeah, you can. I'll leave you to figure it out. Okay, because obviously a 3-input NAND gate is a secondary operation, right? I mean, because remember, our Boolean algebra basically says that all I need for all of Boolean algebra is an OR operator which takes 2 input, an AND operator which takes 2 input, and a NOT operator. And now we showed that, hey, I don't even need that. All I need is a NAND operator with 2 inputs, because then I can implement NOT and OR out of it. And therefore, all of Boolean algebra, and therefore, as a consequence, all of computation, all of mathematics, all of anything which is computable can be done using a supply of 2-input NAND gate. Now, that doesn't mean you're going to do it that way. It's not a very efficient way of designing things, but one could in principle. Any question? Okay, so let's move on. So I'm now going to touch upon certain things which are really kind of matter of definition, but they are useful. So there's a concept of dual of a Boolean function, right? I mean, a Boolean function I can write down as an expression, or I can make a circuit in terms of AND gate, OR gates, and NOT gates and all. So we say that the dual of a Boolean expression is obtained by simply replacing, wherever I have an AND, I'm going to replace it with an OR. Wherever I have an OR, I'm going to replace with an AND. And if I have the constants 0 and 1 appearing in the expression, which they might, that is constants, just like in regular algebra, you can write x plus 2, I can certainly write x or x ANDed with 0, or x ANDed with 1 and all, right? So I will replace 0 with 1, 1 with 0, OR with AND with OR. And now I'm going to get a new expression, right? I mean, this original symbolic expression is replaced by a new one, and that is called the dual. And we indicate the dual with this subscript, superscript d. So this was my original expression, right? You see FAB is equal to A and B or B and C. The dual of this is wherever and I replace it with an or, right? And wherever I had the or, I replace it with and. There were no constants here, so I didn't have to worry about it. So this is just blind substitution, right? I mean, I can imagine if you were writing a software package to manipulate these expressions, this is just look for all the simples of the type and, replace them with or, and replace all the ors with the ands. Okay, so that's the definition. So let's say if we give you this function. Can anyone help me with what the dual of this is going to be? So what is ft?
X or not Y and not X or Z.
Good. Okay, so it's just mechanical, really. Nothing terribly deep about it. But the reason we defined it is because Boolean algebra has a very interesting property, which is called as a duality property. And what it says is, you just read it, dual of a function applied to the complement of the input variables equals the complement of the function. Okay, so remember, I have a function and I can also define the dual of that function using that rule I described. And it's basically saying that if you apply the dual function to inputs which have been negated, then it is the same as complementing the function applied to regular inputs. In other words, dual of f applied to not A, not B, and not C is the same as applying f to ABC and then taking the negation of that. Now, let's say f was simply and. Then now what is a dual of and? Or. So it's saying or of not A, not B, not C is the same as not of and ABC. What is that called?
De Morgan's theorem.
Exactly, De Morgan's theorem. So De Morgan's theorem is just a special case of this duality property. Okay. So anyway, so why is this duality property true is, of course, a much trickier thing to prove. Now we are into kind of making more general statements about the properties of the algebra. So if you're interested in finding that out, if you are kind of inclined towards those kind of things, just Google and you'll find kind of why the duality property holds. So De Morgan's law or De Morgan's theorem is a special case of this duality property. We have not proven the duality property. Okay, so I just would like to mention, I have not proven duality.
Professor.
Okay. Yeah, go ahead, please.
Does the complement just mean a 0 is a 1 and a 1 is a 0?
It's a NOT gate. Yeah, exactly. Complement or negation or inversion, we are kind of use that all have the same meaning. Okay.
Does that also mean that the dual of a function applied to the normal input variables, not the complement, but the actual input variables, equals the same value of the function?
The dual, if you apply the dual of the function, so let's say you apply f of d to a, b, c, then it is going to be not of f applied to not a, not b, not c, right? I mean, all I'm doing is I'm relabeling a, b, c to be not something, right? I mean, so that's what it will look like.
Thank you.
Okay, great. So let's again look at this thing. So what's the dual of this function? Anyone help me out, please?
Not X or not Y and not Z.
Good. What's the complement of f? Well, complement of f is not of not x and not y or not z, right? So that's one way I could do, right? I literally took the complement of the whole thing, or I could do the complement. Remember, what did it say? That the dual of the complement of a function is the complement of f is fd applied to the dual. So I could also write it as not of not x, then not y, and not z, right? So it would look like this, and you should be able to prove that the two are equivalent, right? I can comment it either way. Oh, duality property tells us that that would be the case, but you can convince yourself about this.
Professor?
Yeah, please.
Wouldn't it be just not x and y, not of not x and y? Don't you have an extra not in the whatever? Whatever
Yeah. No. So what I'm doing is the following. So the first version of complement, this is version 1, is basically is basically taking this whole expression, okay, and then applying the not to that, right? So that's a not of f. The other way I can do the not of f is to say that it is it's the dual applied to the complements. So the dual is like this. So wherever I have x and y and z, I'm going to replace in the dual. I'm going to replace them by not x, not y, and not z. So this expression is obtained from the dual. Okay, so I have not, and then inside x, I had x or not y. It becomes now not x or y, and then not z becomes z.
I'm so confused. What are you trying to do there?
Okay, I'm writing complement two different ways, right? I can write the complement by literally just taking the complement of f.
Yeah.
Okay, so in the first case, all I did is I took the expression for f and then added a complement in front.
Mm-hmm.
Right? In the other case, I made use of the property which says complement of f is take the dual function, and wherever I had a, b, and c, I'm going to replace it by not a, not b, not c. So here I had computed the complement. Complement was, I computed a dual, and a dual was this function, right? But this is dual of x, dual applied to x, y, and z.
Oh, and then you just take and
then I replace y and z by their respective complements, right? So this is fd applied to x, y, z, whereas this guy is fd applied to not x, not y, not z.
And the middle is just not of f of x, y, z.
That is what the duality property tells us. So we would expect that the complement that we obtained by simply taking the negation of f and this new other expression which we obtained by applying the dual function to not x, not y, and not z, we would expect that the two are the same. So one should be able to show that this expression out here, this one, and then this other expression, they are the same. Okay.
Oh, okay. Right.
Yeah, you can try out the truth table to convince yourself that's the case. Okay. Okay, so let's moving on. Another definition. So there is something we are going to encounter a lot in the next few lectures, something called min term. Min term of n Boolean variables. So let's say I give you n Boolean variables. Let's say I give you x, y, and z as 3 Boolean variables. So the min term, basically a min term of n Boolean variable is an expression that ANDs together all those variables either as they are or in negated forms. So like, for example, if I give you a function f(abc) and I say, what are the minterms of its inputs, abc, then all these expressions I have written, a and b and c, a and not b and c, not a and b and not c, and so on and so forth, they're all minterms. And I need to have all those three letters appear, a, b, and c. So there has to be all of them. So like, this is not a minterm. If I simply write a and b, not a minterm, because it is missing c. But those symbols a, b, and c can either appear as they are or in negated form. So how many minterms would be there for ABC?
Would there be 8?
8.
Yeah, exactly, 8 minterms, because each variable has to appear either in native form or in negated form. And so 2 times 2 times 2, 8 minterms. So how many minterms are there if I had n variables? Well, what I was asking you, it will be 2 to the power n, right? Okay. Now, if you think of your truth table, each row of the truth table is really corresponding to a minterm, right? Because I go through all the patterns. Like if I was doing the truth table of this function, then I will have 8 rows corresponding to each possible combination of A, B, and C. So minterms have a correspondence to the rows of the table. There's another definition called, another related concept called max term. Max term of n Boolean variables is an expression that ORs together all the variables in direct or negated form. Remember, minterm ANDed them, this one ORs them. So A or B or C, A or not B or C, and so on and so forth. And of course, the same properties hold true, right? 8 of them or to the power n of them. So let's, so I mentioned that how these things correspond. So if I write, so let's say I give you the function of 4 variables, A, B, C, D. And I'm saying that now let's write them down in the, where leftmost bit is going to be 0 and the rightmost. So think of the inputs as kind of a 4-bit number, and the least significant bit is A and most significant bit is D. And I write them like this, and I can assign row numbers, right? I mean, so in fact, probably all of you have at least some familiarity with binary numbers. So basically all I'm putting is the value of the binary number, like, right? So 1010 is the number 10. 1010 is a binary number whose value is, numeric value is 10. I can write the corresponding minterms, so like in the corresponding max terms, like this. So if you think about 0000, when is 0000 results in a true value, when not D and not C and not B and not A. So minterm, basically, I'm going to define it that what minterm gives the true a value true when A, B, C, D or D, C, B, A are all 0. So I kind of write that out here. And for max term, I'm going to write down that max term, which gives me the value 0 when D, C, B, A. So in this case, the max term for 0000 is going to be D, C, B, A. And I'm going to play the same game. For 0001, what would be the minterm which results in a value of 1? So it would be not D and not C and not B and A. What would be the max term? Well, max term would be D or C or B or not A. And so essentially what's happening is minterm, as you know, is and then wherever we have a 0, the variable will occur in a negated form in minterm, and wherever the variable is 1, it will appear in a negated form on the max term. So I can write all of these down, kind of fill the whole table.
Professor?
Yeah, go ahead, please.
So is a minterm supposed to output a 1 and a max term is supposed to output a 0?
Correct.
Okay.
And you'll see later on why do we do it that way. So the purpose behind this, right now, these are just definitions. Okay. And I'm establishing a correspondence between the row of the truth table and a particular minterm.
Professor?
Yeah, go ahead, please.
Why is when the input is 1, 1, 1, 1, the I'm trying to find where the minterm is D, C, B, and A, like all N.
Yeah, I see I kind of screwed up out here. I think my minterms are messed up. DCBA. Yeah, okay, I know what happened. Where did I make the error? I have made an error out here. So 001, 0010, 0011, 0100, 0101, 01. So up to this point, yeah, I think I made an error out here. And then these have to disappear. Yeah, I think I cut and pasted from the previous rows and then messed up the minterm. Sorry about it. I'll circulate the fixed slides. So 100, 1001, 1010, 1011, 1100, 1101, 11, yeah, and this guy. Okay, so wherever I have put that red little thing, you scratch out the knots. Thanks for catching it. Okay, so with this corrected truth table and the corrected entries for minterms, now I'm going to give these minterms a name. So I'm going to call a minterm which appears as row number I as minterm number I, and I'm going to designate that with a little m I. So in this particular case, not D and not C and B and not A is the minterm M2. And likewise, we do the same thing with max term. A max term which appears in row number I is called max term number I, and because it's max, so I'm going to use the uppercase M, big M. Okay, so this is just a naming convention that we adopt. So again, we have a strategy for putting minterms into specific rows, and we are going to label them in that manner. Yeah, go ahead, please.
So basically, what you do for the minterm and the max term is you look at whether it's a 0 or 1, and accordingly either negate or not negate it for the variables, and then for minterms you just put ands, and for max terms you put or.
Yeah, because minterm we define as and, so and max term we define as or. And if I give you a minterm, let's say I give you the minterm whatever, not D and not C and B and not A, then you, wherever the variable is in a negative form, you put a 0. Wherever the variable is in the positive form, you put a 1. And now it will, so not D and not C and B and not A will be 0, 0, 1, 0, and you put that minterm in that row.
So then what's the use of putting it, is it just a way to go from the binary form to logic gate form?
Well, right now it is simply I'm giving each minterm a unique name.
Oh,
right?
Okay.
That's all I'm doing right now. But of course, the intuition is that if the variables have the value, so by the way, again, bear in mind the same error that I had in the previous slide over here. But let's say my inputs were 0, 0, 0, 1. Then at that point, minterm number 1 has to be 1. Right?
Say that again?
If it so happens that my circuit had the input 0, 0, 0, 1, D was 0, C was 0, B was 0, and A was 1, then we know minterm number 1 is going to have the value 1. Right? Because minterm number 1 is defined as not D and not C and not B and A.
So then, well, I mean, that expression for a minterm or a max term should output like a 0 or a 1, right?
Yeah, it's a Boolean expression. So like any Boolean expression, it will have a value 0 or 1, right?
So then how do you know what it is? Like,
well, because you'll be given the inputs, right? I mean, so at your circuit at any given point in time will have a particular values assigned to the inputs. So let's say your circuit had the value D equal to 0, C equal to 0, B equal to 0, and A equal to 1. Then at that point, minterm number 1 will be 1, right? Because minterm number 1 is the expression not D and not C and not B and A.
Oh yeah, well, I'm just saying that the way you've defined it right now, if you have those inputs for DCBA and the minterms defined like that, then the value of the minterms is always going to be 1, right?
Well, but on the other hand, if the input was 0, 0, 0, 0, then minterm number 1 would be 0.
Oh,
right?
Okay.
So essentially think of it like each minterm corresponds to a specific, each minterm will be true for just exactly one input pattern.
Oh, so it's like the like the one hot representation kind of thing.
Well, I'm not sure. I mean, I would call it that way, but it's basically, again, it's basically saying that for each each possible input pattern, there is a corresponding minterm, so that the minterm outputs a 1 only when the inputs have that value and 0 otherwise.
Oh, okay. All right. Thank you.
It's like a matchup, right? And likewise, maximum does the other way.
Thank you.
Okay. So one thing you would notice is that the complement of a minterm is the respective max term, right? So let's say I take the complement of the 0th minterm, so it would be right. So let's say maybe instead of 0, let's say let's say max term number 5. So it is 0, 1, 0, 1, the 5th row. So that's why we are seeing D not C, B not A. And that is equal to the negation of the corresponding minterms. So by De Morgan's theorem, in more generally, M of I is the same as, is equivalent to this. Okay, so that just follows from De Morgan's theorem. Okay, so once we have defined maximum and minterm, this is just the property just follows. Now, where does this lead to? It leads to something very important, which are called normal forms. And the idea is that they're called normal forms because these are a standardized ways of writing any Boolean function. So there are 2 normal forms of Boolean functions. I have an incomplete first sentence. So basically what I wanted to say was a normal form of a Boolean function is an expression that will always be written in a particular standardized way, right? So that is, it's if you write a function in a canonical form, then there is just exactly one way you are going to write it, so that a lot of operations become easier. I'm going to fix this thing. I'm going to fix this. So see new slides. Okay. So, but for us, there are 2 particular normal forms that matter. So normal form is a general concept that in mathematics, right? We write something in the normal form means I'm just writing it, that there is a unique way I can write this thing. So disjunctive normal form is basically a form in which I'm only allowed to have an expression which consists of a bunch of minterms which are ORed together. And since, remember, and OR are often referred to as product and sum, so this is often referred to as sum of product form, okay, or disjunctive normal form. So for example, I could have f of ABC, some function f, written in this manner. So out of the 8 possible minterms, it is true for 3 of the minterms. So it's almost like I can look at those rows where the function had a true value, and then I OR together those minterms, right? Because when the input takes value corresponding to that row number I, then the corresponding minterm has to have the value 1, right? So, and remember we said that a given minterm will have a value 1 only for a given row of the table, the corresponding row of the table. So literally what this is saying is that f of ABC is true when row number 111 is true, or row number 100 is true, or row number 101 is true. So it's kind of just stating a very intuitive thing, right? That a function is true if the input belongs to row number I and J and K. We define it this way. One thing one has to be careful out here is, I'm sort of going to go back out here, which is row number 2 or which is row number 5 depends upon how we are ordering the variables. The order matters. So you in the problem, I would specify that consider the input in terms of DCBA. If on the other hand, I had taken the input to be, let's say, BCAD, then things get shuffled up, right? I mean, so then the ordering will change. So very important that you follow the order, or if you are doing it, then state the order so that someone reading your design knows what is minterm number 5 mean really. Okay, going back out here. So disjunctive basically says minterms ordered together, and conjunctive normal form is when you have several max terms which are ANDed together, and in which case it is called as product of some form. So in this example, if you see, this is a max term, and this max term corresponds to which row? Remember, so for min terms, when the value is 1.
The 0th row.
0, 0,
So-
0.
Arish, so it corresponds to 0, 0, 0. Okay, so you write. So the idea is that conjunctive normal form consists of max terms, and then they're ANDed together. Okay, so these are just definitions of the normal forms. Usually, again, my this is supposed to point to disjunctive. Okay, so this, when if you hear simply normal form, it's usually referring to the disjunctive normal form. Okay, so why use normal form? The
Hold on,
reason is
Professor.
Yeah.
Professor, could you go over what a POS, product of sums, is again?
it's basically ORing together, ANDing together a bunch of max terms. Right? So each one of these is a max term. And remember, we define max term as what? That is an expression which ORs together all the variables either in the direct form or negated form.
Thank you.
It doesn't have
Right.
to be all
So
of them.
it's all of them, absolutely. That was a very critical point we made, right? That if you go back out here, right? So, like for example, A and B is not a minterm because it does not have C. So it has to have all of them. If I give you a set of variables, then minterm should have all those symbols present. Likewise for max term. Okay. Again, I mean, it's not the question. This is how we are defining it. Right? You could imagine kind of a consistent framework where maybe we have some different definitions, but for our purposes, in standard Boolean algebra, this is how we define. Okay. So,
Professor?
Yeah.
Yeah, just to be clear, the definition for each minterm, like let's say M2, or for each max term, let's say capital M6, will change if you change the order in which you define the term, right?
Absolutely.
So
Absolutely.
M2 for ABCD will be different from M2 for DCBA.
Correct.
Okay, all right, thank you.
Professor, could you repeat the definition for normal form one more time?
Sure. So there are two normal forms. Disjunctive normal form basically says write down the function as a ORing of a bunch of minterms.
I just meant the thing that you in the slides that you're going to change.
Oh, okay.
Yeah.
Yeah.
Your definition.
Basically, a normal form of a Boolean so in mathematics, normal forms means a unique way of writing something.
Okay.
So basically, so that's what it's going to be. Okay, so it's a form of a Boolean function, expression that has a unique representation.
Professor,
Mm-hmm.
when you mentioned the sum of products and product of sums, if it was just a term by itself without a product or a sum, would it still be considered normal form?
Yeah, I mean, you could imagine I have a function, let's say FABC equal to A or B or C. Then it is what form?
It would be conjunctive.
It would be conjunctive. If I give you a function which is FABC is A and not B and C, that's a disjunctive form, right?
Mm-hmm.
So because it has a single minterm. So yes, you can indeed have functions which have in its disjunctive form just have one minterm, and in the conjunctive form have only one max term.
Okay, thank you.
And for that matter, you can have zero minterms, like the function f of ABC equals 0.
Would that be both disjunctive and conjunctive?
And that's an interesting one. So think about it. So let's say we have f a b c equal to 0. So it obviously has no minterms, right? All rows are 0. The more interesting one is if I give you the function if f of abc is 1. Technically, it has 8 minterms in its disjunctive form, right? Okay, because all the rows, but I guess the other interpretation would be, this is an edge case, so I'm not sure what the convention would be. That does it have 0 minterms or does it have 8 minterms? And likewise, if I give you a function fabc is 0, then maxterm you can either say it has 0 maxterm or it has all the 8 maxterms. Okay, so so that's a corner case. I wouldn't worry about it. Okay.
Okay.
So so why use normal form? Because it's unique. Each input variable appears exactly once in each turn, and so it makes comparison of functions easy, right? I mean, if I tell you, you give me some function, and then from that I convert it into let's say a disjunctive normal form, and you give me another expression, and from that also I derive the corresponding DNF form. Then I can now compare, right? Because I can just see whether the set of minterms in one DNF form and the set of minterms in another DNF form, are they the same? So it makes comparison easy. So remember previously I talked about how can I compare two functions, and I had given you 4 strategies. Well, there is a 5th strategy, which is reduce both sides to the corresponding, let's say, DNF form, and now compare, not just list the minterms they are, right? Because we have given you a way of naming minterms. So I can do comparison very easily if you ask me to see whether 2 functions are equal or not. In a sense, what we are saying is the disjunctive normal form is basically the set of those rows where the function, in the truth table, where the function takes the value 1. And the conjunctive normal form is the set of those rows where the function takes the value 0. So that's all we are doing. So let's go back to an example from the previous lecture. This was a thermostat example, but the key thing is that we know in this particular case it was about controlling the fan and all, and we see some rows are 1. Okay, so what is the normal form? Now remember, if I say nothing, then it's a disjunctive normal form. So so how would we go around doing this? A disjunctive normal form is terms which are minterms which are ANDed together, right? I mean, they may have more minterms, right? So we focus on the rows which have an output 1. So I can, let's say I take this row. This row corresponds to, now again, ordering matters. So I'm kind of defining that the ordering is A1, A0, B1, B0. That's how I'm going to look at the order. So this is basically saying that A1 is 1, A1 is 1, A0 is 0, B1 is 0, B0 is 0. So the corresponding minterm looks like this. And then I'm going to look at each such row and I'm going to OR it together. So you see these trailing ORs, right? Okay, so I have 6 rows. So you will see 6 minterms corresponding to each one of those rows. And then I'm ORing them together. So going from a truth table to a DNF form is super easy, right? I just write down for each row which has, where the output was 1, the corresponding minterm, and I can write it more compactly. I can basically say, so now you can see that 100 is row number 8, and so on and so forth. So I'm basically saying it's row number 8, 9, and 12, 13, 14, 15. Okay, so and oftentimes more compactly we can write it like this. It's basically saying, remember the summation sign is for OR, so it's basically saying all together the minterms number 8, 9, 12, 13, 14, and 15.
Professor?
Yeah.
Could you explain why you're focusing only on the rows with output 1?
Because if I took a minterm where the output was 0 and I put it in this OR statement, then whenever let's say, for example, let's say by mistake, you put this, the minterm corresponding to, let's say, 0010 also as part of this. then if the input was 0, 0, 1, 0, that minterm would have a 1. And since you are ORing it, then the function will give output 1, but that's not what you want.
Wait, what do you mean?
I mean,
So like the
see, what am I doing? I mean, if you intuitively look at a truth table, when is the function 1? The function is 1 when the inputs correspond to row number 8 or 9 or 12 or 13 or 14 or 15. Only those rows.
yeah.
So literally, I'm saying row 8 or row 9 or row 12 and so on and so forth, right? That's literally what the truth table is saying. So I only want those entries and the input is in row 8 when minterm number 8 is true, right? That's 1-to-1 correspondence. If minterm number 8 is true, then the inputs must correspond to row number 8. There's no other choice. That's how we define them.
Wait, I thought that minterms always have an output of 1 though.
No, why would I have it otherwise? Think about it. If the minterm always had an output 1, then that means it's a constant function. It cannot be an expression, right? Minterm is an expression, right? Like I may have a minterm which is A and B and not and not C and not D, right? When would this minterm be true? It will only be true if A is 1 and B is 1 and C is 0 and D is 0, right? That's the only time it will be true. So it can't be that minterm is 1. Minterm is 1 only when there is a specific input pattern. Minterm number 8.
So for the DNF form, you want something that has an output of 1. That's why you.
I'm not sure what you mean by that we want an output of 1. We want, for DNF form, I want an expression for the function where the expression is of the form minterm, ORed with another minterm, ORed with another minterm and all, right? I want an expression for the function which is written in the form where I'm ORing together. OR is called disjunction, so that's why the name. I'm ORing together a bunch of minterms.
Okay.
But the minterms you select are the ones which correspond to those rows where the function has the output 1.
Okay.
Okay. So basically, if going from truth table to DNF is very easy because you look at those rows where the output is 1 and then take the corresponding minterms. I can play the same game with conjunctive normal form. Remember, conjunctive normal form has max terms. So this is a max term, right? Max term is always of the form where I OR together things, and then I'm going to AND together a whole bunch of max terms. So this time around, we are going to focus on those rows where the output is 0. So as you can see, kind of conjunctive normal form focuses on a different set of rows. So in this case, the rows where the output is 0. And basically what we want to say is the following, that we are going to take the corresponding max terms now, and then I'm going to AND them together. So in this example, the max term corresponding to row number 0 is A1, A0, B1, B0. Max term corresponding to the first row number 1 is A1, A0, B1, not B0, and so on and so forth. That's how we had defined the max terms. And so this is the corresponding conjunctive normal form, and we can write it more compactly like this. We can say F is equal to max term number 0 ANDed with max number 1, ANDed with max number 2, and so on and so forth. Or even in a more compact form, I can write it like see, shown out here. Now, what's going on out here, right? I mean, so here by focusing on, so let's look at, let's say row number 0, right? So row number 0 corresponds to when A and B are both 0, right? So A1 is 0, A0 is 0, B1 is 0, B0 is 0. So what will happen? If I am at row number 0, then the corresponding max term will have the value So let's say let's say I correspond. Let's say I have an input pattern corresponding to row number I. Then by definition of max term, the corresponding max term, namely max term number I, will be 0. So like for example, in our case, let's say the input was let's say I look at this row. Okay, that's row number 2. So A1 is 0, A0 is 0, B1 is 1, and B0 is 0, right? And the corresponding max term is this guy. And that will take the value 0. So max term number I becomes 0 when the input corresponds to row number I. And you can check that I'm doing A1, which is 0, ORed with A0, which is 0, ORed with not B1. B1 is 1, so not B1 is 0. So I have 0, ORed with 0, ORed with 0, ORed with 0. So the whole max term is 0. And I'm ANDing together a bunch of max terms. And the AND function has a property that if any max term in my list is 0, then the function is 0. Right? The whole expression would be 0. So what this gargantuan expression is doing is basically saying I'm ANDing together a bunch of max terms, and if I happen to be in a row which corresponds to where the function is supposed to be 0, then one of these max terms would be 0, and 0 ANDed with a whole bunch of 1 is still 0, so therefore I'll get a 0 as what I want. If on the other hand, let's say the input was this guy, let's say row number 14, 1, 1, 1, 0, then none of the max terms in my list are going to be triggered, right? So they will all have the value 1, and I will have 1 and 1 and 1 and 1, all I'm basically going to be ANDing together a bunch of 1s, and therefore I will get as an output 1, which is what we want. So the DNF is focusing on rows which are 1s. CNF is kind of doing exactly the opposite. It's focusing those where we are focused, where the function takes the value 0. Intuitively, let's say I give you a truth table. Can you suggest to me what would you do how would you decide whether to use DNF or CNF as a first blush? Let's say your goal is to write a small expression. So what criterion would you pick to select CNF or DNF?
So we would use DNF if there are fewer outputs with 0, and we would use CNF, or fewer outputs with 1, and we would use CNF if there are fewer outputs with 0.
Exactly. Yeah, absolutely. I think there was someone else speaking up. So were you going to say the same thing?
Yeah, I was going to say you look at which one has like the least amount of zeros or ones.
Exactly. Yeah, exactly. So both of you got it. So basically, kind of, if I'm a truth, just give me a sec. So if a truth table dominated by 1s, then the expression for CNF would look smaller, right? It's going to be a product of just a few max terms, and other way around. If it's somewhere in the middle, then of course you can go either way. Yeah, go ahead, please.
So the output of a CNF should always be 0, and the output of a DNF should always be 1. Is that how it is?
Output of CNF would be whatever the output of the function is. Remember, CNF is giving you a expression which is exactly equivalent to the function. Right?
Oh,
let's say,
okay.
Right? The CNF and DNF are a particular way of rewriting the expression of the function. So this expression is equal to f. It's going to behave exactly as f is behaving. But
where f is like your Boolean algebra function, like the original function that you had.
Yeah, it's the normal form for that function. Yes.
Oh, okay, that makes more sense.
Yeah. So would we prefer writing the functions in disjunctive form, because you said that was what was normally referred to as the normal form?
Excuse me. Well, firstly, I mean, you are my sneezing. It would depend upon the context. DNF certainly is more common. Excuse me. Yeah. DNF certainly is more common, but of course, in any given setting, you might be asked. One of the things is DNF generally corresponds to NAND gates. You will see later on why. Like if you have an expression in DNF form, then you can implement it very directly with NAND gates. And if you have a expression in CNF form, then you can very directly implement it with NOR gates. So I guess sometime your choice is dictated by those considerations. Okay. Excuse me. Okay, so let's move on. One thing is sometimes you will see this expression even during the course where I say what are the min terms and max terms of a Boolean function. So unfortunately, there is kind of even the textbook kind of uses it in two different ways. So sometimes when we say, oh, what are the min terms of a Boolean, of a specific Boolean function, let's say I give you a Boolean function and I say, what are its midterms? Sometimes it means that it's referring to all the possible min terms and max terms that the input can form. So like if I have a function which has 3 input variables, A, B, and C, then saying what are the min terms of that function means we are referring to all the 8 possible min terms. And sometimes when we say min term of a function or max term of a function, then we specifically refer to those min terms where the function is 1 or those max terms where the function is 0. So like, for example, let's say we have this function that I have written out here. Let's see. Yeah, scratch that B. So according to usage 1, how many min terms does this function have? Well, it has 3 inputs, so it has 8 min terms. On the other hand, according to usage number 2, how many min terms does it have? Well, there are 2 possible min terms where the function takes a value 1 because it's a ORing of 2 min terms. So in which case we will say it has 2 min terms. In this course, when we say what are the min terms of a Boolean function or maximum of a Boolean function, we are going to refer to this. And if we mean all the min terms and all, then I would say the min terms of the inputs of the function. Okay, so this is just to disambiguate because I noticed the book at various places uses it in these 2 different ways. So that can be confusing at times. So let's try this. What is the dual of this function?
It would be x or not y and not x and y.
Good. Now, I'll leave it up to you to attempt to write it in a distinctive normal form. Well, let's make a start. So I'm going to take the cheap, easier way out. Okay, I'm going to okay. So if x and y are 0, 0, then well, what will happen if y is 0? So if you look at this expression, if whenever y is 0, output is 0 for fd. Okay. Whenever no, if y is whenever y is 0. Okay. So whenever y is 0, because of this guy, we have an output as 0. Whenever y is 1, then if x is 0, right, then again the function is 0. So this is 0. And otherwise, we are left with, so if we are left with 1 row, so x and y are 1 and 1. So this is 1, this is 0. Sorry, yeah. I messed up. If x is 1, I'm sorry. So okay, so now the only thing we are remaining is x is 0, y is 1. So So this is not 0, and we are here, and x is 0, or not y, but y is 1. So this is 0. So the whole thing is 0 or 0 and okay. So this is 0 and 1 and 1. This is 0. So the dual of this function is always false. Okay, so not terribly interesting. Okay, I think I probably messed up out here. I guess I probably intended a and
Professor?
but anyway, that doesn't matter. Okay, yeah, go ahead, please.
So if we were to ask to find the disjunctive or conjunctive normal form, would doing tables be easier, or is there a way that we can use the properties of like Boolean algebra? Like
yeah. So a great question, and of course, the way of doing the table was my lazy way out here in the middle of a lecture. Of course, it will not scale if you have. I mean, by the time you hit even 3 variables, let alone 4, things can drawing the table with 4 variable table can be painful. So you have one should ideally try to do it in a symbolic manner by kind of using those properties and expanding it out. Actually, getting to DNF form and all is usually not too hard because you're just expanding it. You're kind of like unrolling everything. Okay, so you will end up with a gargantuan expression, but you can do it. Normally, though, what happens is out here you basically make use of there are software packages which let you manipulate Boolean functions. I mean, that's how one would do in real life if one were to do it. But using the expressions is using the expression by writing it by hand can be pretty painful. So I guess short answer is if you're doing that paper and pencil, if it is small enough, then do the truth table approach. It's a lot easier. If there are too many variables, then you will not have a choice because truth table would be too complex. But then by that time, you should probably be using some package anyway. Okay. Remember, the purpose out here is for you to understand the principles, not that in real life you are going to be doing large functions in this manner. But you should understand what is going on. So in a problem set and all these kind of settings, when we ask you, it will be manageable in a form that's manageable. But specifically for your question, normally, I mean, these tools and all internally do it by simplifying the expressions. The reason they do it that way is because if they were to resort to enumerating the truth table, then it will take exponential amount of effort, right? Because they have to list every entry of the truth table. So if you want a fast enough software, you have to do it most, the algorithm has to be smarter. It should not enumerate everything. Okay, so yeah, I'll let you figure out at your home. I mean, just try some of these expressions to see what form you end up with. Okay. By the way, in Logisim, you can create the circuit, and then there is under one of the menus you will find that it can give you expressions as sum of product and product of sums. So you can check within Logisim.
Professor, I was having a hard time downloading that correct version of Logisim. Do you mind if I talk to an officer about that? I was having a hard time downloading Logisim 3.3, but Logisim 2.7 works. Logisim 2.7 doesn't have that, so can I talk to an officer about that?
2.7 is obsolete. It is like almost a decade old.
Yeah.
So unfortunately, we'll be relying on features that are well beyond 2.7. At the very least, you should be using what I had listed as the latest stable version. Mm-hmm. Okay, which is I think 2.14.6 or something. So that's the one.
Okay.
Are you like they are directly downloadable from GitHub, corresponding GitHub website, so it shouldn't be hard. I'm not sure why you're running into problems. Like, is it just a network issue?
I don't know. I'll talk to an officer about it, I guess.
Yeah,
So I've worked on it.
Yeah. Let's delegate these kind of questions to officers. Okay. So mapping equations to logic diagrams with gates. So remember, ultimately we want to create hardware. So let's proceed with that. So I have now these primitive gates. and, or, and not, and or often are available in more than 2 input variety also. Implementation cost tends to be proportional to number of inputs. So that's a good rule of thumb, okay? And the reason is the following. A NOT gate uses 2 transistors. Lower down, right? I mean, I'm referring to now, remember gates are made using transistors. So NOT gate in CMOS technology uses 2 transistors. A K input and K input NAND and K input NOR, they use 2 times K transistors. These are your native gates. Okay, so now what would be the cost of AND? AND would be a K input, so therefore K input AND would be 2K plus 2 transistors, because it needs a NAND gate followed by a NOT gate. So in CMOS. Okay, so actually our basic primitives of Boolean algebra, and, or, and not, are not quite hardware aware, because AND is more expensive than NAND in CMOS. Okay, so anyway, but rule of thumb proportional to number of inputs. So now how do we take a expression, arbitrary complicated Boolean expression, and write it down into gates? And the idea is that you start with the top level process operator, okay, and then recursively go into each sub expression. So let me tell you what I mean by that. So let's look at this expression. Let's say I give you this expression: f a b c is a and b, or b and c, or a and c. I can write it equivalently like this. I can say it is an OR of AND of AB, BC, AC. So I have like a 3 input OR gate. Sorry, I messed up. Apologies. Right, I can have sort of written it in a function type form, right, in programming language terms. So if you think of it this way, my outer operator is OR, right? That is the top level operator, okay? And the fact that I'm doing 2 ORing is just saying I have a 3 input OR. And then the next level down is AND gates. So that kind of gives me the same. My outer level thing is OR, and it has 3 inputs, and then I have 3 ANDs, okay? And then I have the ABCs. So I can take any expression, however complicated. In this case, it has just 2 levels of this, but you can basically apply this principle. Always start from the highest level, which means closest to the output, and then kind of work your way backwards. So let's take this example. This is a function ABC, which corresponds to minterms 1, 5, and 7. So I kind of write them down in this expression: minterm 1, 5, and 7. So let's see, did I mess it up? Minterm 1, 0, 1 is 5, 1, 1, 1 is 7, and 0, 0, 1. This should be absent. Okay. Okay, so not A, not B, not C. This is M1. This is M5, and this is M7. Okay. So outer level is OR, and then I have 3 AND gates, but I also now need inverted version of some of the A, B's, and C's. So that's what you see out here. Okay. I think. Okay, yeah, I kind of obviously messed it up here. So let's modify this example a little. I'm going to, because my diagrams are written for the incorrect operation. So, okay. I'm going to call this thing M0. Okay, so I'm going to work with that. So let's say our function was M057. Then I would have that, and then I'm going to keep fixing it. M0. Do the outer level OR gate, then I do the next level of AND gate. So they correspond to like this guy corresponds to this, then I wire them up. Okay, so usually what happens is for all the inputs to your chip, let's say you will have both. You will immediately kind of create negated versions of it so that you can use them wherever you want. So see how what I've done is that some of these things are feeding into multiple places, like this place, which is not B. I need it in two places, here and here. So that's why it's feeding to two gates. This is implementing M0. This is implementing M5. And this is implementing M7. Okay, so so I can go from expressions to gates relatively easily. One other thing I wanted to say is the following. Remember I told you that CMOS technology, OR and AND are harder, and that NAND and NOR are cheaper. Using De Morgan's thing, can you think of converting the circuit somehow so that I only use NAND or NOR?
Can you use De Morgan's law to convert everything?
Yeah, so how would you do it? So can you suggest to me what would I do? Can you think of an easy way of modifying the circuit so that everything is either a NAND or a NOR? So here is the trick, right? What if I put two inverters back to back, what do they do?
They just pull out the inverted in front of it, right? In front of the gate.
Normal input.
No. So what is the Boolean function they implement, right? I mean, if I feed an input to a inverter to a NOT gate, and then take its output and feed it into another NOT gate.
It's just the input itself.
It's a what?
It's the input itself.
Yes, input. It's an identity function, right? So it leaves things unchanged. So I can add an inverter here, and then I can add an inverter here, right? No effect. I can add an inverter here, and I can add an inverter here. And I can add an inverter here, and I can add an inverter here. Now I have NAND gates, and I have this funky looking gate. De Morgan's one, it says OR of complement is the same as complement of AND. So this is same as a 3-input NAND gate. So I have transformed that original circuit, the DNF form circuit. This is DNF form, right? I have translated that into something which can be done just using NAND gates. Okay. So that's why, I mean, one of you had earlier asked this question, I mean, why DNF and all. So if I have supply of NAND gates, then a good starting point is DNF. Let's look at another example. Let's say fxy is this. Well, okay, I guess I'm not solving these. I'm leaving them for you to figure out. Okay, so anyway, let's do this one. Okay, so what would the circuit look like out here? So what's the outermost operation here?
Not.
Say it again, your voice chopped up.
Is outer operation not?
Outer operation, not. No.
Isn't it OR?
Okay, which OR?
The one in the middle, the one right before, like it says Y and then parentheses close or not, yeah. That one.
This is OR, right? I mean, so remember, so to the first student, remember not is a high priority operator, right? So this not is really applying to this parenthesis. So I can really put an extra pair of parentheses out here, right? And likewise, this not is the second not is applying to this, so I can really put it like this. So usually if you are sort of not sure, add as many parentheses as needed until you are clear. So this is the OR operator. So OR is the outermost one. So that's F. It takes two inputs in. So let's put two placeholders. So the next one, it is taking the not of something which is an AND. So it's really a NAND gate, right? This guy. And it's taking X inverted on one and Y on the other. The other guy inside this parenthesis again has an OR gate, right? So or one entry is Y and the other entry is an AND gate. Oh, sorry, this thing is a NOR because there is a negative sitting out here. So it's a NOR. Okay. So okay, so this other input to my OR gate, to NOR gate, is this X and not Z, right? So it is this guy with an X. So you can say I can connect it together out here, and Z, right? So the circuit is going to look something like this. So basically, going from an expression to circuit is pretty. It's just a matter of directly translating. Okay, you can not very dissimilar from when you write a software program. The compiler parses this thing. So there are very standardized, pretty routine algorithms where you take an expression and then you kind of translate that into circuit. So straightforward. So the trick really is to first come up with a good small expression and then translate that into the gates, because translation to gates is just mechanistic. So gates in CMOS. So remember I said CMOS is the technology which is used. So it's a dominant technology for making digital systems. And the gates in this technology come in two varieties. So the type of transistors that this thing uses is something called MOSFETs. Stands for metal oxide field effect transistors, but nowadays the metal part is a bit of a misnomer, but doesn't really matter. The main thing is that there are two types of transistors, N types and P types, which basically depend upon whether they have made of material which has an excess of electrons or paucity of electrons. But what it translates into is that N-type transistors turn on when the voltage at their controlling input is high, and P-type transistors turn on when the voltage is low. Now, none of this really matters to us for the course really, but what it boils down to is that because of the way CMOS works, the basic gates in CMOS are inverting. Okay, so they are things like NAND and NOR and inverter. And to create an AND gate, you have to take a NAND gate and put an inverter in front. So I made that point earlier on also. So even though Boolean algebra started with AND and OR and NOT as kind of the foundational operations, but if we were to be designing a Boolean algebra today for purposes of designing computers, probably we would have defined NAND and NOR to be the basic operators, okay, not the other way around. So as a consequence of all of this, one thing, because we often need to invert signals, so instead of drawing things like this all the time, this shorthand notation emerged, right? We just put a bubble wherever we need an inverter. So the bubble can be put at the output of a gate, like out here, or at the input of the gate. So these bubbles really are basically just saying inversion. And also there are a variety of reasons having to do with robustness and noise and all that. Oftentimes, like if you have to make a choice, should I implement this signal so that it is normally high or normally 1 or normally 0, it turns out that oftentimes one choice is electrically better than the other. So you will often see these kind of signals where they are deliberately designed to be inverted. That is, like this guy, for example, is control input, which is here. It is designed to be that when I want this is something called tri-state buffer. We will not see it, but it is designed to be active when the signal here is low, signal at this controlling wire. So that's why you will often see, like if you look at data sheet of a chip and all, many of its important signal, they would be like this enable bar, which is basically saying that enable has to be, that pin has to be 0 in order to enable the hardware, or ready bar, which basically means, again, in order, it would be, if it is ready, then it will actually make the signal low. So essentially what's happening is, for these signals, the value which we consider to be important, the truth value, is actually 0 in electrical terms. So all of these are artifacts of the technology. But De Morgan's theorem help us go back and forth very easily, right? So in this example, let's say I wanted this guy, the tri-state buffer, to be enabled whenever enable A and enable B were both true. Okay, I want it to be active only when both those signals are true. But my controlling signal here had a bubble in it, so I will use an AND gate to kind of do it, right? So if you look at what this logic is doing is this NOT and this NOT cancels out, and essentially what we are doing is we are saying this tri-state buffer is enabled when both enable A and enable B are true. So when you're reading circuit schematics and all, kind of bear in mind that, like, if you see something like this, enable bar, it's really saying it's a signal which is inverted. My true signal is enable, but the actual signal I'm using in the circuit is the inverted version of it. So whenever I actually want it to be inverted, I need to pull that signal to 0. This bubble pushing that I showed earlier is extremely important. So we can easily sort of play this game of introducing a pair of bubbles and then push them out. Okay, so for example, if I have this AND gate, I can so the solution is you can apply this trick. You change. Let's say I give you a circuit, okay, and I tell you change AND to OR gate or OR gate to AND gate. Right? I give you a circuit and you let's say I had an AND gate and you want to convert it into OR gate. So the rule is change the logic gate to AND to OR 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 to AND, and then add bubbles to inputs and outputs if they were none previously. So like, for example, I had this AND gate. I can replace this AND gate by an OR gate, and since it did not have bubble on any of the inputs, I add bubbles to all of, any of the input and output, I add bubbles there. So if you think about it, these two are exactly the same. Okay, and the reason they are exactly the same is because I can apply De Morgan's to the right hand side, so I can replace not input, whatever, negated input being ORed with an AND with the output negated, and then that will cancel out. You can convince it. So let's look at this example. It's an OR gate where A was inverted, B and X are non-inverted. So I will replace the OR by the and then wherever there was no bubble, I'm going to put the bubble, so at B and X, and wherever there was a bubble, I'm going to remove it. Again, these two circuits are the same. So you could go back and forth, do this transformation very easily. Let's look at the final one. I had an OR with two bubbles, so I'm going to change OR to AND, remove the bubbles, so E and Z, they're gone, and F did not have a bubble, so I introduced a bubble out here. So and again, the reason we are able to do all of this is because of our friend De Morgan's theorem. Okay, so to summarize all of this, what we saw in this module is Boolean operations. We saw some of the properties. We saw that gates can represent each other, and really all we need is not a supply of large enough supply of 2 input NAND gates or 2 input NOR gates, and you can do anything. You can literally do anything that can be computed can be built using just those. We saw some definitions: dual, min-term, max-term, DNF, CNF, and we saw how to map equations to logic diagrams. So now what we are going to do is, thus far we just saw how to map it, but we kind of ignored the whole issue of efficiency, right? We saw that we can write Boolean functions as expressions and all, but we kind of saw also one of you had asked a question like, is it cheaper one way or the other and all. So next set of slides, we are now going to examine how to make efficient things. So that brings us to module 5. How to do things efficiently. Okay, how to do good design. Okay, so that's what we are going to focus on now. Okay, so this corresponds to chapter 6 now. Okay, so let's look at this example called we just did the recap. Okay, so one thing, by the way, I would mention is that some of what we are learning out here is really for the sake of understanding the principles. What happens in real life is that people who understand these principles very well, then they write some software tools which encapsulate those principles, and then the hardware designers actually use those tools. So some of you, some 20 of you are taking the honors seminar, and there we are we are looking at that perspective, like what those tools are and how do we get to use them. But in this main class, we are really going to focus on the principles part of it. So the industry practice, like I said, is really meant for designs which may have billions of transistors or billions of gates, and you can't do it the way from a first principles approach, but it's important to understand. So let's look at something that we want to implement. So we want to implement a function f. It takes 4 inputs DCBA, and it is true if the input DCBA, when we view it as a 4-bit number, then its value is either 1 or is a numerical value which is a prime number. Okay, so if I think of DCBA as a 4-bit input, so for what values would it be 1? Well, so we are saying 1, and then prime numbers 2, 3, 5, 7, 11, 13, right? Because I have 4 bits, so I can go up to 15. So these are going to be the prime numbers. So if I were to, actually, yeah. Just, is anyone, okay. I'm going to just quickly go over it here, that if you have never seen Boolean numbers, they work exactly like decimal numbers, except that the place value, instead of being 0, instead of being 1, 10, 100, 1,000, and so on and so forth, it is 1, 2, 4, 8. So if I give you the bits like 1101 or 1010, we just give them positional values like that. So like 1010 represents, it has the weight 8, 4, 2, 1. So it becomes 8 times 1 plus 2 times 1 equals to 10. Okay, so so that's so when I say what is prime, that's what I'm referring to. Okay, so now if I look at this, then I can assign numbers corresponding to these, and sorry. Okay. So what we are saying is that if it is 1 or prime, that's when we want it. So if you see 1 and then 2, 3, 5, 7, 11, and 13, those are the rows where I have the output as 1. All the other rows, the output is 0. Okay, so if I want to write it as a DNF form, can someone quickly tell me what the DNF form look like? Remember, in DNF, we have minterms. Which minterms do we care about?
The ones that are 1.
The one which are 1. Okay, so summation of minterms number, and literally the spec follows, right? 1, 2, 3, 5, 7, 11, and 13. Okay. What about the max terms? Well, in max terms, we focus on the rows which are 0. So it would be row number 0, 4, 6, 8, 9, 10, 12, 14, 15. Okay. So firstly, given a truth table, it's super easy to write these things. Okay. So let's go back out here. So so this thing is true if input is 001 or input is 0010. So I kind of just make the list of all those rows where it's 1, and then for each one of those, I can basically write down the corresponding minterm, right? So DCBA, shoot, did I mess up? Yeah, as usual. Sorry. Okay. So So I can write these expressions corresponding to each one of these minterms, and then finally I can just write it down like this. Okay, or you could have just straight away come down here. Okay, but so we have seen enough examples of that. But the reason is that these are the minterms corresponding to those values of the input where the function f takes on the value 1, right? So we have to exhaustively list them, and the way we had defined the problem, it made it pretty super easy out here to do it. And then I have to translate that into gates. So what's happening, right? It's a DNF form. So the outer operation is an OR, right? It's a sum of products. So outer operation is the OR. This is a sum part. And then this is a product layer. And then how many AND gates would I have? Well, each one of them. So firstly, since I have what, 1, 2, 3, 4, 5, 6, 7 minterms out here. So I'll have 7 AND gates. And each AND gate will need all the 4 inputs, either in regular form or negated form. So like first one is corresponding to minterm number 1. And then likewise, this is minterm number 2, minterm number 3, and so on and so forth. This is minterm number 30. Okay. So I can literally just go ahead and write this, right? So from that spec to truth table to this circuit is kind of really super straightforward. Now, of course, this is corresponding to a normal form. So I have a circuit, but I have no idea whether it's a good circuit or a bad circuit, right? I mean, is it the best I could do? And that's really the question we would explore. Now, intuitively, I mean, it seems to have a lot of gates, right? I mean, I have this out of 16 rows, 7 of them are 1. So that's why I ended up with a lot of gates. So what the game we are going to play is to try to merge things. Okay, some of these gates we will see can be merged together. And let's see how that gets done. So firstly, I'm going to write a truth table, which is abbreviated. And this was a comment that one of you had made during last lecture also, which is, do I really need to write down all the rows? Can I just write down the rows where we are 1 and then say otherwise 0, right? So that's what I have done. I've kind of only focused on those rows where the function takes the value 1 and otherwise 0. So now let's look at these 2 rows. Okay. So these are minterms number 2 and 3 respectively, and they differ only in one place, right? So if you my apologies. So here, unfortunately, I think I forgot to change the slide. So we have and not out here. Okay, the main thing is that the first colored row corresponds to not D and not C and B and not A. And the third colored row corresponds to not D and not C and B and A. And what does it look like? I mean, if I look at these 2 expressions, this initial part is common to the 2, right? Here and here. So really I have an expression of the form, if I call this thing X, then I have an expression of the form X and not A, ORed with X and A. And using one of those properties, if you remember, this is equivalent to saying it's X. So which is why this merge. So this A and not A, they are merging together. So things which differ only in 1 bit, minterms corresponding to row numbers where inputs are differing only in 1 bit, I can reduce them. So I get this. So where I had 2 4-input NAND gates, now I have 1 3-input NAND gate. Right? So because remember, in our original one, each one of these rows corresponded to an AND gate of 4-input each. And now I have replaced 2 of them by a smaller AND gate. So I'm better off both in terms of count and number of inputs that the AND gate has. And remember, I told you earlier that the cost of an AND gate is proportional to number of inputs. So really, I went down from a cost of 8, let's say, 4 plus 4, to a cost of 3. Huge reduction. Can I play this game with any other row?
could you do it with number 5 and 7?
Exactly. So I can do it with 5 and 7. What about anything else?
11 and 13.
So
Will we do 1 and 5 instead? So we can do. No,
okay,
never mind.
I can absolutely. So I can do 1 and 5 because they differ only in one place. Okay. So I certainly can do these things, absolutely. But hey, why stop at just one bit change? Can I do something even more? Can I be more aggressive about it? Okay, so firstly, yeah, so I kind of already said this stuff. So one can replace, one can merge rows. So the way in truth table terms we often write this thing when we merge is that we say 0010 and 0011 after merging becomes 001x, where x means it could be either 0 or 1. Okay, so a product term like this, which does not have all the inputs present. Remember, after I merge two minterms, it has fewer variables occurring in it, right? It's no longer a minterm because it doesn't have all the inputs present, but it is called an implicant. It's called an implicant because it implies the function. So that's the idea, that whenever, in our case, whenever not D or not C or B takes the value 1, then the function is 1. So this implies the function. So it's called an implicant. So this is a new definition we saw. So what other minterms can be combined? So I can combine 5 and 13. I can, and the others that you sort of saw. So we are going to come back to this. Let's see how are we doing in time. We are 1 minute past, so I'm going to stop out here. And I promise you I'm going to fix these typos that are on my slides and upload them. Okay. Any questions before we hang up for the day?
Professor?
Yeah.
When would the first homework be assigned?
Yeah, the first piece set should come out on Saturday or Sunday. Okay.
Okay, thank you.
So for this slide here, what's preventing us from combining 5 and 7 and 5 and 13?
You absolutely could, and we will see next time that it actually helps.
Okay.
And you would actually even see that in some cases, I'm not sure about this, looking at this function, but you can also combine 4 things or 8 things or 16 things depending on. So you can do more than just 2.
Okay, thank you.
Yeah. So does combining it just make it a shorter expression? That's all?
Well, it's not simply that's all. I mean, it's reducing our cost significantly, right? I mean, I guess depends on where this thing is on things of importance. But I have replaced. I replaced. It was what, 3 and 5, right? So I have replaced 2 4-input gates with 1 3-input gate. And if I can do this game a lot, I can reduce the circuit down quite a bit, right? So,
okay.
Right? I mean, so it's
yeah. In terms of cost, that makes sense. That's right.
So it is really about the silicon area and actually also the speed. A 3-input gate is going to be faster than a 4-input gate. Okay. So speed, power, area, are kind of all the things that one would care about when optimizing hardware. Basically get benefit from this. Okay. So that's kind of any other questions?
Is this the system how like a computer software will interpret a truth table? Like, is this like the basic idea of that?
Yes, except with the huge caveat that the software written to manipulate Boolean operations do not make use of truth tables, because truth tables are not very efficient. So they are written using, remember I had shown those binary decision diagram last time around. So they work in these other data structures which tend to result in faster algorithms, but they're kind of conceptually equivalent. Okay. Anything else? So one thing I would really encourage is come to the office hours. Thus far, I have had 4 students who have dropped by the office hours. If nothing else, come and chat and just introduce yourself, but also any questions about logistics or lectures or whatnot. And likewise, I mean, we have office hours 4 days of the week between me and the TAs. So do come and interact with us. And also tomorrow during the discussion section, the TAs are going to go over some of this material again, so solve some problems. So,
excuse me, Professor. Could you go to the last module on slide 32? Sorry, slide. Yeah, slide 32. So, sorry.
Okay.
Yeah. So I think, I don't know if I'm doing this right, but the first function has 6 terms. And then when you go to the second one, the first one has 5 terms. The second one has 6 terms.
Yeah, I think
it has to be one more A and B and C. Because I think
you're saying yeah, but okay. So in going from here to here, the thing is I can just add as many A, B, and C as I want, right? I mean, X or X is the same as X. So I guess I didn't explicitly say it, but going from the first to the second, kind of just did that. Yeah.
Okay. Thank you.
Okay. Okay. So we'll hang up for now then, and if you guys have any further, if any of you have any further questions, yeah, just ask on Piazza. That's probably the easiest way so that everyone gets to see it easily. And also, I'm sure all of you have noticed, I'm also uploading everything on CCLE as well, so you can go for videos and material wherever it is more convenient to you through Piazza or CCLE. Okay, well, goodbye everyone. See you on Tuesday.
Thank you. Goodbye.
Yeah, thanks everyone.